everybody. Welcome to the Neptune room. It is my delight to be able to present to you Asanka, who's going to discuss from WSO2, who's going to discuss with us today cloud native architecture, decentralizing reference architecture for cloud native applications, as a matter of fact. With that, since we're running a little bit behind, I'll go ahead and just jump right into and have Asanka go ahead and get started and fill us up with your delightful knowledge.
Thank you. Thanks, Bill, for the introduction. Good morning, good afternoon, good evening, everyone. It's 1:30 a.m. for me. I'm based in California, but still kind of very enthusiastic to share this topic with you. So before jumping into the topic, I'll give a quick introduction about myself. So I'm coming from a strong product engineering and product architecture background. So I spend most of my time on distributed computing, middleware development, as well as architecting different type of middleware products, as well as I'm a contributor to open source world a lot. I'm a Apache committer. Then I started solutions architecture practice at WSO2, and now as the chief technology evangelist, I am telling the WSO2 story. So today I'm not going to discuss about WSO2. If you are interested about the company and the products, you can go to our website wso2.com and find more information about the topic. So what I'm planning to do during next 40 to 45 minutes, explain about the reason behind why we created this new pattern. And then second thing is how we created the pattern. And then again, go in detail about the architecture pattern as well. So if you are interested reading more about the topic, I have put the URL to the complete specification. You can go there and read the complete specification as well. So after I published this architecture paper in 2018 summer, I got invited to many architecture conferences and other tech events. When it is used to be physical, a lot of people came to my session by looking at the topic. But when I looked at them inside the room, I got this feeling. People were looking at me and then thinking whether this guy is smoking. Because the microservice architecture is well established and people are working on cloud native application. So the question was why you need the new architecture style. Actually, I was not smoking. There were a lot of reasons behind this effort, why I came up with a new architecture style. The first motivation factor is I found there's a mismatch in the industry. Architects are looking for an reference architecture to build these applications, but the available architecture styles are not fit into that particular requirement. So that mismatch was my first motivation. Then when you look at most of the architecture styles are centralized and layered. So this is a problem. Even you might be using microservice architecture, but when you fit into an enterprise, it fit into one layer of the entire spectrum. I'll explain that in detail in a different slide. So the problem with this centralized and layered architecture, when the technical architecture become layered and centralized, the organization structure also fit into that because these teams will work on these specific areas. And when you have a layered architecture, layers create gates and gates are blocking the flow. So that means the productivity and the efficiency of these teams are very low. As example, in this particular diagram, if the integration team wants to get something done from the security team, they have to communicate and wait. And if the messaging team wants to get a table or a database created, then they have to talk to the data team and wait. So like that, there will be a lot of wait time and killing the productivity in this particular approach. Then if you talk to architects, they show very nice diagrams, like well aligned, using the latest technology, very clean. But if you look at the enterprise, it looks like this because we purchased many applications and applications created many data repositories. Inside the enterprise, it looks like this, and we can't throw these systems and we can't throw this data. We need these data and systems to run enterprises. So we need to find a way that how we can connect this brownfield and greenfield. Another problem that I identified, most of the reference architectures are addressing one part of the story, either brownfield or either greenfield. So what I thought, when we are defining an architecture pattern, it should address brownfield as well as greenfield, because if you look at an enterprise, the brownfield is larger than greenfield. And if you are a startup, then you are lucky because then you can start with greenfield applications, but that is not the reality we have in most of the organizations. Then the another thing that I identified, most of the reference architectures labeled as reference architectures, but those are reference implementations. Why I'm telling those are reference implementations, those reference architectures are bound to a specific a vendor and specific vendor technology. So what I thought, when we are defining the reference architecture, it has to be completely technology neutral and vendor neutral, that you should be able to pick the technology and the vendor based on your technology selection and implement your applications. Then another thing is underutilization of the technology. It's just like you keep your best players on the bench while you are losing the game. So as an example, when I talk to architects, they say, okay, I have a Kafka cluster running, but I can't use it because my architecture doesn't support it. And sometimes they say, I have a Kubernetes cluster running, but my application architecture doesn't support it, so I can't use it. So how we can have a flexible architecture that can utilize these technologies was another motivation factor that I had. Then another thing that I identified, there's a gap between the architecture development and deployment, or the between architect, developer, and the DevOps engineer. So I thought there should be a common way that you should be able to connect these three user personas as well as activities done by each and every user. So basically connect the architecture, development, and deployment, and take an artifact across these three levels and have a commonality in between these three layers. Then another thing that I identify, the dependency management. With decentralization and microservices coming into the picture, you see many moving components in your enterprise. And if you look at this Uber diagram that they have published, that they call it as a Death Star, when you have many microservices, enterprise might look like this. So we need to have some governance across the architecture, and the reference architecture that you are using should be able to cover or handle that governance as well. So let's look at the architecture patterns, a history, and what we were using so far. So we started with monolithical architecture, that everything was bundled together. Then it moved to the two-tier architecture with the data and the database technologies got advanced. Basically, the user interface, business logic move away from data. Then the three-tier architecture came, most interesting era, that the user interfaces, business logic, and data got separated. And there were many sub-architecture patterns came with 3T architecture, like model view controller is a good example. Then service-oriented architecture came by wrapping the business logic inside services and APIs, and there were many sub patterns came with that, like event-driven architecture, web-oriented architecture, so on and so forth. Then around 2012, we moved to microservice architecture, and now we are at this cell-based architecture, that what I'm going to describe today. So if you look at this diagram, what happened is layered and centralized architecture moved to more segmentation, and then now completely moved to a decentralized approach. So these are architecture diagram that I drew around 2009 or 2010, around that time. And it was a very productive diagram, and we used this to build many systems. And if you look at this diagram carefully, it is not a typical layered architecture diagram. This is two-dimensional. What I did, added all these system level layers in one dimension, and introduce this life cycle of an application, as well as quality of services like security, governance, and monitoring into another layer, or not another layer, another dimension, and improve this. Even still, some of the organizations are using this particular architecture. So it was a very useful diagram during that time. But we identified one of the projects that we were working in Seattle, Bellevue. So basically that project failed. They were using agility a lot, agile team, but they expose around 100 APIs, they connect 60 message flows, and build around 80 services, and in number of databases got connected. And this application or the system was multi-tenanted, and they had 3 active tenants from day one. But unfortunately, even they were following agility, the first release went into production after 3 years, and the business had to throw the project away because the usual story, after 3 years, business requirements had changed and they were not able to use the system. So we were wondering what really happened. If they are following agility, why they couldn't deliver? Then the reason was, even team was working on agile principles, the architecture wasn't agile enough. So we thought we need to find a solution for that a layered architecture doesn't work anymore. Same time, microservices came into the picture, and there were a lot of theory behind microservices during that time, but few organizations started using microservices in reality. But one common thing we identified, all these organizations, they put a layer on top of core microservices. Netflix called it as APIs, Uber called this as edge gateways, eBay called this API facade pattern, and even Gartner introduced this concept called mini services on top of microservices, which act as a composite service. So let's look at what is this service concept and how it affects in business and technical domain. If you look at a service, and the technical definition of the service is pretty simple, that you just write some code and you annotate it, and based on the framework that you are using, it will become a network accessible code. So what you will be doing, you will have a binding for that service that's basically listening on a port, and then you have a message format, how you communicate with that, as well as how you access it. That's basically the service contract. That can be like a SOAP service, or it can be a RESTful service. But the business doesn't care about that. What business is looking at, it is looking for a solution for a business problem. When you try to build a solution for a business problem, one service might be not enough. So you need to do connectivity of these services, so composition of these services. So we have to put a gateway or a composite service on top of the services. You have to connect these services. Then when it comes to microservices, again, the technical definition, it's not changing that much. And if you look at a code, it just like you write some code and then you annotate it, or use the semantics of that particular framework that you are using to write the service, and it will become a network accessible code. It's basically that you divide that monolithic service into small pieces based on the scope, not based on the size, because that is very, very important, because people trying to divide these large services based on the size, but the correct way to do it is based on the scope. Again, business doesn't care that you write monolithic services or you write microservices. What is business looking for is a modular components that is addressing a business problem or providing some business capabilities. When you try to provide business capabilities, again, you have to connect these microservices. That's where a composite service or a gateway coming into the picture. That's why all these examples I used earlier were using a layer on top of that. So during that time, 2012 or early 2013, the enterprise architecture inside this organization looks like this. So basically you write microservices, but microservices became another layer, and the same layered architecture started continuing. Some of the organizations, they had some workaround for this to give more autonomy. So they have these partitions within each and every layer, and I call it as a segmented architecture. And this is a lot better than the typical layered architecture. But then again, if you look at it, it is layered. Some organizations, they extend this thing that I call it as platform of platforms, that each and every business unit, they deploy the entire platform as a private deployment, and they try to use it. But if you go inside the platform, again, it is layered. So we hit this dead end. Whatever the improvements that we are doing, it is a layered architecture and it is becoming centralized. There's no way out. So we thought we have to find a new way as well as think in a different angle. So we did a lot of research and kind of narrow down our research into a few areas. First thing is about quantum computing, and then we identified there are really good concepts behind Kubernetes architecture. So we identified those. And interestingly, we were focusing on biology and system biology as well. And that's where the name cell came into the picture, and you will identify why we were interested on these biological concepts. So the cell is the basic structure, right? To any living being built with cells. And if you look at a cell, there's a membrane and there are other components which help to connect each and every cell and create a system or a structure to provide some kind of a capability. So that's where we picked this biological concept, because we thought an enterprise architecture looks like that, because enterprise is an adaptive, a complex adaptive system. So I think this cell analogy fit in nicely to that. So let's look at the cell-based architecture in detail. So in the cell-based architecture, we have these atomic units that we call it as a component. So component can be any runtime or any workload that you run in a cloud environment or in a hypervisor-based virtualized environment, or even on bare metal. So the component can be anything. It can be a microservice, it can be a service, a database, message broker, anything that you run, a UI or whatever that you require to build a system, we treat it as a component in this architecture concept. So the collection of components create a cell. So we call cell as a unit of enterprise architecture, and it's a collection of components, as I said, and there's a cell gateway, and inside the cell you will find many components inside that, and there's a clear boundary for a cell as well. And cell is independently deployable, manageable, and observable as well. Those are the kind of characteristics that this cell will contain. And we talk about this grouping of microservices earlier, right, to provide some business capabilities. So same thing comes here, that grouping becomes a cell, and that is how we identify there's a need that you have to group these cells and put a cell gateway on top of your microservices. And cell to components, what's the ratio? In many cases, or common case, it is one to many. But there can be some cases that it can be one-to-one as well. As an example, if you make a cell with a message broker, or if you create a cell with a database, it can be one-to-one. And cell required connectivity because connectivity is the core in a distributed architecture. So I'm using this concept of a control plane, data plane, and a management plane. So my best example to explain this concept in detail is a rail system. In a rail system, the rails rails can treat it as the control plane that carries the signal of the network. And the data plane is the train compartments where the passengers, or in networking, the messages are going up and down. And there's a management plane that control or configure this route of the trains, as well as in networking, the management plane route create the configurations of these different type of signals for the control plane. So the same concept apply here. Inside the cell, there's a local control plane and local data plane. And outside, there's a global control plane, global data plane, and a management plane. So I call the local control plane and local data plane as the local mesh, and the outside control plane data plane as the global mesh. And if you are familiar with service mesh concept, this is service mesh plus plus, because there are two meshes that you see in this architecture style. And the connectivity of the cells, any ingress call coming to a cell should hit the gateway. That is the only way you can communicate with the components inside the cell, that you can't directly communicate with the components inside the cell. So the cell gateway act as the gatekeeper. And the egress calls can go outside from a component and hit another gateway of a different cell. So you can use these patterns like sidecar, adapter, ambassador to facilitate the egress call. So I'll repeat it again because it's very, very important that any ingress call should hit the cell gateway, but egress calls can go out from the components, but go and hit another gateway of a different cell. So these are where API first architecture, because the components expose the capabilities as APIs, as well as cell expose the capabilities as an API. And it can be any kind of an API, a RESTful API using HTTP or gRPC, or a push API using events like JMS, MQP, SMTP, or it can be streaming like Kafka or MQTT. So you, based on the capabilities that you are providing and the style that you want to expose your APIs, you can decide what type of API that you are exposing. So the cell gateway adding many advantages. Since any communication goes through one of these gateways, you can have policy enforcements, like the gateway can act as a policy enforcement point, or any other additional policies like throttling policies you can enforce at the cell gateway level. With that, you get observability automatically, because now all the communication will happen through these gateways. So if you enable observability at the gateways, you can capture observability data and feed into your observability platform or analytical platform. Even you can use machine learning and AI to kind of improve the user experience based on the data that you capture from your observability layer. The security of the cells is very, very important. Basically, there are two patterns that we identified based on the implementations that we have done. The pattern one, you are using the local control plane, and the STS inside that particular cell can provide all the decision-making capabilities for authorization, authentication, and entitlement. So like mutual authentication, self-signed tokens, those kind of concepts can be used here. And in some cases, pattern 2 will come in handy as well. When you need additional attributes, you can go to the global control plane and fetch those attributes from a identity provider. And those attributes can be cached in the local control plane to make it more efficient, because security is a performance killer when it comes to certain situations. So you can optimize by caching some of these security decisions. So pattern 1 or pattern 2 will depend on your implementation and use cases, but those two patterns can be supported in this architecture style. Then the developer experience is very important, because what a developer likes to do, they like to go through that particular cycle, and that's where the productivity come into the picture. A developer can do certain activities. They might create a brand new cell from scratch, or they might have the microservices already written, and they might create a cell out of the existing microservices. They might update an existing cell, or they might create a new version of the cell, depend on the infrastructure capabilities that they will have. So the life cycle of the developer will not change. As I explained, they will write, they will build the code, they will commit it, they will test it, and they will debug it. And once a test or the unit tests are passed, they will push the code into a remote repository. Then the CI/CD will kick in, and it will deploy a component into a cell, or it will redeploy the entire cell. And if you are in a containerized environment using a container orchestration system like Kubernetes, you should be able to deploy an entire cell without any issue. But if you are in a traditional hypervisor-based environment, you might have to deploy a component without deploying the entire cell. And if your CI/CD process is not matured enough, then CI/CD task can taken care by a release engineer, and he or she should be able to run the scripts and deploy the cells or components into the production environment. The life cycle of a cell looks like this. Each and every component contains a version, as well as each and every cell contains a version as well. So that way you can manage these different environments, as well as based on the usage, you can even release new versions of the cells and components while sticking to the previous versions in case if somebody is using this. That's where the observability will be really useful. Based on the observability data, you can decide when to deprecate a component version or a cell version based on the usage. Then this particular architecture creates something called a structured agility, because you get agility at different levels. The first level is at the component level, because each and every component contains a version. The second level comes at the cell level, because cells contain a version, so you should be able to version the cells. Then the entire enterprise level, you will have agility as well. That's where these three levels of agility increase the overall agility of the organization. That's where the structured agility will come and help for these teams. So those are like the fundamental concepts about the components, cells, and then versioning of the cells. What's the developer experience on this particular architecture side? But then again, when it comes to the enterprise, it's more complicated. So let's take a look at how cell-based architecture can incorporate it into your enterprise architecture. So if you look at it in a very high level, it looks like this. You will see various type of cells running inside your enterprise. So that is the ideal model and the ideal situation. And then cells will expose the capabilities, and top of that, you will build your applications, and inside the cells, as you see, various kind of components will run. So based on the implementations that we have done, as well as looking at the enterprise architecture needs, we categorize these cells into few types. And these types are like well enough to design a complex enterprise architecture. But if you have to introduce new cells, the architecture style is flexible to do that. So if you look at different type of cell types, logic cells are the user or the experiences that you provide for end users. So it can be different type of microservices and the first thing is called the logic cells. Those are the logics that you contains inside these particular cells, and those components can be microservices, functions, micro gateways, and lightweight storages. Then you get integration cells like micro ESBs and integration microservices, lightweight storages, and caching kind of components will go inside the integration cells. Then you will find the legacy cells as well, because as I explained, we can't avoid legacy applications. Excuse me. So we had to deal with the legacy application. So we can use legacy cells to cater the existing systems and any legacy services as well. Then the external cells are the cells that doesn't own by the organization. They might be utilizing the functionality, so it can be a SaaS application or a partner system. And there can be data cells like relational databases, NoSQL storages, file-based storage systems, message brokers. All these things will go inside the data cells. And then identity cells like IDPs and user stores can go as components into identity cells. Then the channel cells, those are the user experiences that I earlier referred as logic cells, but the correct type is channel cells. So you will have web applications, mobile applications, or edge like IoT related applications inside the channel cells. So let's look at a reference implementation. I call this as level 0 reference implementation because in my definition, level 0 is the vendor and technology neutral implementation. In this particular example, you will see employee cell that connects to a user store and a database and a HR system as external cell. Then you have an order cell and a customer cell like that, and all these different kind of cells are exposing this functionality into the applications, and those applications built at the edge utilizing the capabilities exposed by each and every cell that you see in this diagram. Then if you look at the reference implementation of this, I have used a bunch of WSO2 components as well as other industry leading components like Nginx as a gateway, Spring as a way to write the components, and different type of deployments like Docker, Kubernetes, VMware, and databases like MySQL, and SaaS applications like Workday, Salesforce, like that. And the icon that you see on in green color, those are Ballerina, a language that we introduce. I'll explain it in a different slide. So what I want to highlight in this slide, like this particular reference implementation that you saw, can be implemented by using different type of vendor technology. So it's completely up to you to pick these components and how you are building the components based on the technology that you would like to utilize. And this is a very human-centric architecture because the agile teams or autonomous teams, or we call them as the two pizza teams, they can define a boundary by using these cells. So cells creates a team boundary very nicely. And you can use like domain-driven design, and a domain can or a subdomain can map to a cell and use it as a cell boundary. And I have written an article in the Forbes Tech Council. I have put that URL down here. And if you are interested, you can go and read that particular article as well. So this is a new architecture style. So as a technologist, the business might come and question from you why you need a new architecture, and then what's the purpose. So that's where the measuring the success will be really important. So I'm using a couple of metrics here. The first thing is the flow efficiency. Basically, you can measure the productivity time by identifying the wait time versus the productivity time. And in this particular architecture style, the wait time will be limited and your productivity time will increase, so the flow efficiency will be really high. And the decentralized componentized architecture will help you to detect issues quickly. That is MTTD, or mean time to detect. And as a result, you can repair these systems quickly. We call it as mean time to repair, or MTTR. So those are three good metrics that you can use: the flow efficiency, mean time to detect, and mean time to repair, in case if you want to prove that what is the impact you are making from this particular architecture style. So if you look at the summary, a cell is self-contained, and the cells are the units of enterprise architecture, and you can independently deploy, and you can independently scale, and each and every cell has a local data plane and a control plane. And if you summarize the architecture, it's a decentralized, microservices friendly, and cloud native architecture style, and it's technology neutral, very human centric, and you can utilize this to build API products as well. So the contribution to this concept came in many ways. First thing is the specification. So you can access it from this URL. And not only that, I authored the methodology to implement the specification as well. Both are released under Creative Commons 4.0. So feel free to send a PR and then give an update. And there are a few other contributions that we have done. Ballerina as a language, a cloud native programming language, if you would like to write the components or microservices. Then WSO2, we provide many cloud native components that you can use to manage the APIs and integrations, as well as identity and access management. Then the last URL called celery.io, that is an experiment that we did. It's a pet project we created when we defined this architecture. So if you want to take a look how this concept running on top of Kubernetes, you can go and look at that particular repo. And it is not an active project at the moment, since it was a pet project, but released under Apache 2.0. So these are my contact details. Like if you would like to continue this discussion, as well as if you want to get more information, you can contact me. Best way is LinkedIn and Twitter. I'm very active on those two platforms. But if you want to contact me via email, this is my email address, as well as if you want to get any additional help, we can provide some strategic consulting as well. So I think we came to the end. We have around, I think, 3 to 5 minutes, I believe. And if you have any questions, I am happy to utilize that time to answer any questions that you have.
Thank you so much, Asanka, for that informative discussion on cell-based architecture. I look forward to checking out some of those links that you posted.
Thank you, and I would like to thank the organizing committee as well as the program committee, and hope it was useful. And as I said, you can connect with me, and I'm happy to take this discussion further if you have any requirement to build an architecture on top of this reference architecture style.